Alright, so we're going to be doing week 5, circuits 2. So first we're going to be covering the basic parts of a circuit. So this was briefly covered in the last video on the physics of a circuit, but we're just going to review that before we move on to the rest of the lesson. So this is a basic diagram of a circuit. First we have the battery, which provides power for the entire circuit, or electricity. Then we have a switch. This is kind of like a door or a latch or something. And basically it controls whether power is flowing through the circuit. So for instance, right now the switch is open, so then the power is not able to flow through the circuit because the wire is not connected. You need to have a continuous wire going through the circuit for electricity to flow. And then when it's closed, then electricity would be able to flow through the circuit. Then we have the light bulb or resistor. This is actually like a diode, and it acts like a resistor, which was covered last week. And then finally, this is a resistor. So now we're going to be going over Boolean logic. So Boolean logic is basically a way to make different decisions. It takes in inputs that either can be true or false, and then it returns an output that can be either true or false. So in computers, for instance, decisions are made based on like electricity. It could be either flowing or not. It could be on or off. So this can be represented by zeros and ones. And the output of this logic is binary, or true or false. This logic is used in circuits. It's also used in programming, and it can be represented by algebra. So we're going to be covering some of the basic or the fundamental functions of Boolean logic. So the first one's the not function, not operator, and it basically takes in either a true or false for the input, seen as x, and then it reverses it. So when the input is 0, the output will be 1. And if the input is 1, the output will be 0. So in, say, a circuit, if there's electricity flowing, then that would be a 1, so x will be 1. But if there's a NOT gate there, or NOT operator, then the output would be 0. Next we have the AND, and this takes in two inputs. Each of these inputs, once again, can either be true or false, 0 or 1, and the AND function basically returns true or 1 if both x and y are also 1. So you can see here in the first row, x is 0, y is 0, then the output xy would be 0. And same thing when either x is 1 or y is 1 but the other is 0, then the output would be 0 because it's an AND operator. It has to be both x and y have to be true, have to be 1. And finally, we have the OR function. And the OR function, or the OR operator, returns true if either x or y is true, or 1. So in the first row, the output is 0 because both x and y are 0. While in the second, third, and fourth row, there's one of the inputs is true in at least one of the inputs. Yeah, at least one of the inputs is true. So then the output would be true, or 1. So next we're going to be going over some logic gates. So Boolean logic can be applied in programming, circuit building, and it can be represented by algebra, as I said earlier. But in circuits, we represent them through logic gates. And this is how your computer can make different decisions. So the first gate, like we said earlier, is the NOT gate. So you can see the algebraic expression of the NOT gate is A with a line over it. So when you write it algebraically, that would be how you express that, A being one of the inputs. And then the symbol is a little triangle with a circle in the front. The little circle in front kind of represents like an inverter of sorts. And then next we have the truth table. So the truth table, like we saw earlier, basically shows all the possible inputs that can go into that gate, and then the corresponding outputs. So in this case, in a NOT gate, it inverts or reverses the input. So a is 0, x is 1, when a is 1, x is 0. So next, we're going to be going over the AND gate. So the AND gate is represented by a, b, right next to it, like kind of like a times b in a sense, in algebra. And a and b each being one of the inputs. The symbol for this is kind of like a square in this semicircle. I'm not sure what you call that, but it takes in two inputs, a and b, and returns one output, which is x. And then you can see the truth table, it only returns true when both a and b are true, or both or one. And then finally we have the NAND, next we have the NAND gate. So NAND gate is basically the inverse of AND. So you'll see in the front, in the symbol, there's a little circle in front of what would be the AND gate. And that little circle kind of reverses the original gate. It inverts it. So you'll see in the truth table, when both of the inputs are not true, or both of them are not 1, then it'll return 1. So for instance, like in the first row, when a and b are both 0, then it's the output's 1. If one of the inputs is 0 and one of the inputs is 1, then the output will be 1. It basically reverses the AND gate. And you can see that's also algebraically, it's like a NOT with the line on top of an AND expression. So AB with a line over it would be a NAND gate, kind of like a NOT AND gate. Next we have the OR gate. So the OR gate is represented by A plus B. So A and B being the two inputs. And this is a symbol. It's, I don't know how to describe that, but you'll recognize it now. And once again, it takes in two inputs and only returns 1. And then for the truth table, it returns true or 1 if any of the inputs are 1. And next we have the NOR gate. So NOR gate, just like the NAND gate, is an inverse of a previous gate. So the NOR gate, as you can see, has a little circle in front of what would be the OR gate. And that shows that this is an inverse of the OR gate. So as you can see in the truth table, it only returns true when both A and B are false or 0. If there is any trues or any 1s in the inputs, then the output will be 0. And as you can see from previously in the OR gate, that's the direct opposite. That's the inverse of it. And then in the algebraic expression, it's the OR gate algebraic expression with a line on top, which shows that it's being inversed. And finally, we have the XOR, or the exclusive OR gate. And basically, this gate, as you can see in the truth table, only returns true when either A or B are true, not when both are true. So it's exclusive to just when one of them are true. So you can see in 0, 0, when A and B are both 0, the output is 0. When B is 0 and A is 1, then the output's 1. When B is 1 and A is 0, then X is 1. And then this is the difference. And when A and B are both 1, the output is 0 because exclusive. That's an exclusive OR gate. And you can tell when a gate is exclusive if there's like a little line in the background or behind the gate. So you can see it looks like an OR gate, but then there's a little line on the left, and that shows that it's an exclusive OR gate. The algebraic expression is like the plus circle. So one thing to keep in mind for all of these gates is that it doesn't just have to be 2 inputs. Sometimes it could be 3 or 4 or more. But as long as the inputs are just zeros and ones, then they can still function. We're just going to be working with gates that take 2 inputs or 1 input in a NOT gate. So circuits are based on electricity and power, like I said earlier, and they can have many different inputs as long as they're either true or false. Each of the inputs are true or false. And then outputs a binary output. So binary means that there's only 2 possible outcomes, 0 or 1. And like I said earlier, truth tables can be used to simulate or represent all these possible inputs and their outcomes. So next, I'll be switching over to writing, and I'll show you how to go over these different types of logic gate circuits using a truth diagram, as we stated earlier. So a truth diagram, remember, can represent all the different scenarios. So in this first problem, we have 3 inputs, right? So we have A, B, C, and then our output, which is Q. Okay. So after we put in all the possible inputs for the truth table, then we're going to go ahead and label these gates. That way we remember what are the different behaviors of these gates. Okay. So to label these, or to put in the inputs for the truth table, you want to put all the possibilities of zeros and ones. So with the common convention, if you have 3 inputs, is to do 4 zeros and then 4 ones in the A, and alternate in the second column. In the last column, you just 2 zeros and 2 ones. So you can see that this represents all the different situations or different combinations of inputs for this output. Alright, so now we're going to be looking at these gates. So let's label them. So the first gate is an OR gate, if you remember from the presentation. So I'm going to make a little diagram here to kind of remind us what does the OR gate do. So making a little truth table here, mini one, A, B, Q. And so an OR gate, as long as one of the inputs is 1, then the output will be 1. So in the first situation, there's 2 zeros and the output will be 0. But the second situation, B is 1, so then output's 1, and third situation, A is 1, there is one input, at least one input that's 1, so then the output will be 1. The last situation, there's 2 inputs of 1, so then the output will be 1. So this is the truth table for the OR gate. Got it? So now we'll label our second gate. So our second gate is an AND gate. So let's write out the truth table for an AND gate. A, B, oops, I made it too big. Q. So an AND gate, both inputs have to be 1 in order for Q to be 1 or to be true. So it'll be 0 in the first situation because neither one of the inputs are 1. In the second situation, only one of the inputs is 1, so it's also 0. Same in the third. In the last situation, both inputs are 1, so then the output would be 1. So now that we've labeled all of our gates and we've also made a truth table to represent them so we can reference it later, now we'll actually go through all the different scenarios in our truth table and then figure out what would Q be. So in the beginning, I suggest labeling on the diagram each of these inputs and then seeing Q from there. Later on, you'll be able to really understand the different behaviors of the gates without having to write them all out, and then you can just write it straight into the truth table. But for now, let's write it out in the diagram. So for the first situation, A is 0, B is 0, and C is 0. Well, if A and B are both 0, let's go to the OR truth table. well, then the output will be 0. So OR equals 0. So now we have our input for the AND gate, because the output of the OR gate is an input for the AND gate. So we have a 0 for the first AND gate input, and then 0 for the second one. Well, if we look at the AND gate truth table, we have 2 zeros for input, then the output would also be 0. So in Q, our output would be 0, and then we write that in the truth diagram. Alright, so now let's move on to the second situation. So the second situation, A is 0, B is 1, and C is 0. Alright, so let's look at our OR truth table. Well, A is 0, 1 and B is 1. Well, that is a 1 for the output, because only as long as one of the inputs is a 1 in an OR gate, then the output will be 1. And then our AND gate will have an input of 1 and an input of 0. So look at our truth diagram again. If A is 1 and B is 0, then our output will be 0. So then Q for this diagram will be 0 for this second situation. So now we'll be just repeating this process for all the other situations. So I'll write that out really quickly, and then you can follow along. Alright, so in this situation, we had an output of 1 from the OR gate, and then an output of 1 from the, or input of 1 for C, so then AND will be 1, because both inputs are 1. Alright, so these are all of our different scenarios, all our different outputs. So now we can see that there's only 3 different scenarios where this logic gate circuit will output a 1. So like in a circuit, like electricity will be able to flow. There's only 3 situations, 3 different inputs where it will result in an output of 1. So now I'm going to show you how to represent this algebraically. So algebraically, we're going to only focus on which situations have an output of 1, okay? So I'm going to Q is equal to, so we're only going to focus on those 3 situations, right? So now we're going to show each of these situations, the different inputs that are required. So the first one, all right, here, right, is when A is 0, B is 1, and C is 1. Well, when you write the equation, you need to invert all your zeros. So A is 0 in this situation, right? So then we're going to invert it so it becomes a 1. So all the inputs are, in a sense, are 1s. You would invert that input. So A will become A prime. So A prime is how you denote that input has to be inverted. So if A is inverted, and then B is 1 and C is 1, then it'll have an output of 1. So remember, this represents an AND expression. So remember, AND gate, the algebraic expression is like XY. It's basically kind of like multiplication in a sense, where the 2 inputs next to each other. That's how you know it's an AND. Well, that makes sense for a situation, because we want to, Q is 1 when A is 0 and B is 1 and C is 1. So it's like an AND statement, right? So in that case, when A is inverted when it's A prime, when it's 1. B is 1 and C is 1, then the output would be 1. So then we're going to do a plus sign, and then write our next situation. Well, remember the plus sign is indicative of an OR gate. So an OR gate has an algebraic expression of x plus y. So that makes sense once again for what we're doing, because we're showing the situations where all the inputs are ands, like those specific scenarios, but then there are multiple different scenarios where Q is 1. So in this situation, or in this situation, then Q will be 1. So now let's write that out. So A is 1 when B is 0, so then we're going to invert that. So B prime and then C. Got it? So when A is 1 and B is 0 and C is 1. And then we have our last situation here. So when A is 1, B is 1, and C is 1. Got it? So we don't need to invert any of them because they're all 1s. So this will be our unsimplified equation representing this logic circuit. So remember that when you make the equation, you're only focusing on when the output is 1. You only care about when the output is 1. Okay, so there's ways to simplify these equations, but we're not going to be covering that in this video because that would take too much time.